The ball moves when a player pushes it away or pulls it toward himself. That's how all things move, when some force is applied to them. A force is a push or a pull exerted on an object. That holds true whether we're talking about construction sites, soccer games, or the movements of the planets. How do you measure motion? The first step is to figure out the position of an object relative to another object, or to the background. For example, the pitcher in a softball game is in the center of the baseball diamond. She is opposite the batter and catcher. To her right is third base, and to her left, first. Behind her is second base. We've identified her position. In softball, the speed of the ball is the distance it travels in a certain amount of time. To describe the motion of an object, such as the ball, we measure three things. 1. Its speed, the distance the object travels in a given amount of time. 2. The direction in which it moves. And 3. The change in speed over time, or acceleration. In this case, the ball travels from the pitcher's hand to the catcher's mitt at a speed of about 60 kilometers per hour. The speed of this car is 100 kilometers per hour. What if you want to describe the direction the car is going as well as its speed? That's velocity, which includes rate and direction. If you say you're traveling 100 kilometers per hour westbound, that's your velocity. If you do not change your speed or direction, then your velocity remains the same. On a clear night, far from the lights of the city, thousands of stars are visible in the sky. Every so often, other celestial bodies are too. In the 17th century, the motion of the planets perplexed scientists. They knew the planets orbited the sun, but why? What prevented them from following a straight path and racing off through space? It wasn't until 1687 that a satisfactory scientific explanation was put forward. In that year, Isaac Newton, an English astronomer, published his law of universal gravitation. Newton realized that the reason the planets orbit the sun is related to why objects fall to Earth when dropped. The sun's gravity pulls on the planets, just as Earth's gravity pulls down anything that is not held up by some other force. Gravity is the force that pulls objects together. It exists between any two objects that have mass. The larger the mass of either one or both of the objects, the greater the gravitational force between them. Because the sun is so massive, its gravitational pull on the planets is strong enough to keep them in orbit. Newton showed that the gravitational force is universal. It applies to any two objects with mass. So just as Earth revolves around the sun because of the sun's gravitational pull, the moon, which has a much smaller mass than Earth, revolves around our planet. Although the moon is about 25% as big as Earth, its mass is only 1.2% of Earth's mass. The moon's gravity is only 1/6 of Earth's gravity. And on Earth, the planet's gravitational pull keeps our bodies firmly planted on the ground. The greater the distance between two objects, the weaker the gravitational force. The force of gravity is strong close to Earth, or near any other massive body, but gets weaker as you go out in space. The astronauts aboard the International Space Station are far enough away from Earth that they experience less gravitational pull. While gravity keeps these cars racing on the track, another force, friction, also plays a big role. At the starting line, the goal is to increase the friction between the tires and the road. More friction means greater grip or traction. Drag racers work at increasing the frictional force between the tires and the road. Before the race, the tires are hosed down. Then the drivers spin their wheels. The tires become warm and actually stick to the road. Because the tires don't have tread, they stick just the right amount, giving them grip at the start of the race. Friction is at work for ordinary drivers too. When a driver puts on the brakes, friction causes the car to stop. Many factors determine the degree of friction between tires and the road. In general, the greater the tread on the tires, the more friction there is, and the easier it is to stop. The conditions of the road also affect friction. The drier the road, the greater the friction between the tires and the road, and the easier it is to stop. There is less friction between the tires in a wet road, making it harder to stop. Other vehicles have to deal with friction too. Trains have steel wheels to reduce friction. Since a train weighs thousands of times more than a car, the rolling resistance is a major factor in determining how much force it takes to pull the train. The train's steel wheels ride on a tiny contact patch. The contact area between each wheel and the track is about the size of a dime. The downside of using steel wheels is that they don't have much traction. Engineers have compensated for this by adding special rims around the wheels to help keep the train on track when going around turns. But when braking and accelerating, traction is definitely an issue. Did you ever notice how hard it is to move a heavy object, but once you get it going, it seems to move more easily? That's friction again. Static friction keeps this box from moving and keeps this object at the top of the ramp. Once the block starts moving, kinetic friction slows it down so that it comes to a stop. Athletes have thought of ways to reduce friction so that they can enjoy a faster ride. Downhill skiers rely on the smooth base of their skis to increase their speed. Waxing skis acts as a lubricant that cuts through the snow more smoothly. In the air, friction is created when an airplane moves through our dense atmosphere. To overcome this, engineers streamline the designs of planes to minimize air resistance. Movement is part of our world. We can measure distance, speed, and direction. We also understand how forces such as gravity and friction affect how fast people and vehicles can travel. As we go about our daily lives, these forces are at work.